Implicit differentiation. So first of all, some definitions. What's the difference between an explicit equation and an implicit equation? So an explicit equation is one where you get the y all by itself on one side, like y equals 3x squared minus 2. And those are the ones that we've been doing the derivatives of so far. They're pretty straightforward. If you wanted to find the derivative of this, 6x, no problem. An implicit equation is one where you can't get y all by itself in only one equation. Like in this case, this circle, x squared plus y squared equals 16. That's an equation of a circle. When you get, whoa, a yellow marker, here we go. When you get y squared by itself, when you go to square root both sides, to get your equations, you have to remember the plus or minus. And so what that does is it creates one equation that's the positive square root of 16 minus x squared, and the other one that's negative square root of 16 minus x squared. So well, the plus or minus makes it two different equations. One equation's with the plus, one equation's with the minus. So if you were finding the derivative here, you would have one derivative where it was plus, and one derivative you'd have to do when it's negative. So it gets a little bit complicated that way. You could do it, right? If I just had the positive part, in the square root, well, that would be the same as 16 minus x squared to the 1/2. And then the derivative, can you see it would be a chain rule? So you'd bring the 1/2 out in front and subtract 1, and then multiply by the derivative of the inside, which would be negative 2x. Can you see that if I had a negative, the other function with a negative out in front, that the y prime would be identical except there would be a negative out in front? So you would get 16 minus x squared, the negative 1/2, times by negative 2x. So you'd have two different derivatives. And in this case, you would say, well, if I had the plus or minus at the front, it wouldn't actually change my derivative. I could have written my derivative with a plus or minus. Now, this example, we could get y by itself in two different equations. We will get some examples where we won't be able to get y by itself. We won't have the algebra skills to do that. So then we develop a technique, and that technique is called implicit differentiation, so we can still find the derivative even if we can't get y by itself. So we're going to look how we would find the derivative of this one using implicit differentiation, even though we already found the derivative by making two separate functions and solving for it. And this is what it will look like. We know that y is a function of x. Even if we can't solve for it, we know that y equals, again, going crazy with the highlighter here, something with an x. Now, we already saw that before. It's the square root of 16 minus x squared, plus or minus. So we know what it looks like, but sometimes we won't know what it looks like. What we're going to do when we do the derivative now is we're going to do the derivative of this whole side, and we're going to do the derivative of this side. So we're going to differentiate both sides separately and then see what happens. Now, our sum and difference rules say that when I'm adding two different things, I can do the derivative separately. So what's the derivative of x squared? 2x. What's the derivative of y squared? Well, it would be 2y if this was d dy. Okay? So you're right. If you did d dy of y squared, the answer would be 2y. But we're doing d dx of y squared. See the subtle difference? We're trying to differentiate with respect to x instead of differentiating with respect to y. What that means is we're doing, here we have y equals blah, 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 right? Does it make sense that y squared would equal this whole thing squared? And if you had to do the derivative of that, how would I do the derivative of this? Well, it would be a chain rule. The 2 would come out in front. I would have x. Ooh, keep that blue. Blue. Never mind. And then, whatever you have in the inside, because it's a chain rule, you would do the derivative of that. Well, what's in the inside? The inside is just my original function y, because my original function of y was something x. We're getting theoretical here and abstract, so I hope you're trying to follow along. So we have some function here, and if we wanted to do the derivative of this, the derivative of this will just be the derivative of y, dy dx. So what we say is the 2 comes out in front, this stays the same. So we do our outside function, and then the derivative of the inside is whatever it would be, dy dx. So now when we're doing d dx of y squared, you will get a chain rule. First of all, you would say, well, my outside function is my exponent, which is a 2. So what does that do? The 2 comes out in front, the inside stays the same, and I subtract 1 from the exponent. So I do get a 2y. But then I still need to do the derivative of the inside. And my inside function is just y. And what's the derivative of y? Well, that's the derivative, dy dx. And this is going to equal the derivative of 16, which is 0. So right here is the abstract concept that we're dealing with in implicit differentiation. It's based on the chain rule. We say y is a function of x. It's equal to something x even if we don't know what it is, even if we can't solve it. In our case, we did solve it. We knew that y was equal to square root plus or minus square root of 16 minus x squared. We were able to do that. So right here, what y squared is, when we're taking the derivative of it, we could do the squared first by taking the 2 out in front and subtracting 1. And then the chain rule would say to do the derivative of the inside, and the derivative of y is just dy dx. Yes? So with the chain rule. Well, let's finish this question just so we have it done, and then let's look at another example, and that might help us see what's happening easier. Something that we can actually do. Anyways, we want to solve for dy dx. Can you see that now, if I wanted to get this by itself, I could subtract x, subtract the 2x on both sides, and then divide by 2y. And you'll get negative x over y as a derivative. Okay? So here is a simpler example. It would, okay, so let's just, as part of this, why is it not the same derivative as the one before? So when we solved for it and got it by itself, we got these as our derivative, right? And you're asking, why is it different? In fact, it is the same, and I'll show you why it's the same. If I would simplify both of these expressions right here, and they'll simplify the same way, the only difference is one has a positive and one has a negative in front. So I'm just going to simplify this one here. Can you see my 2's are going to cancel out? Okay? And here I have a 16 minus x squared to the negative 1/2. So if I want to rewrite this one, what am I left with on the top? I'm left with a negative sign and an x. And on the bottom, I'm left with a square root of 16 minus x squared. Okay? And in the other one, I would have exactly the same thing, except I have another negative in there. I'm just going to put that negative on the bottom. It needs to be somewhere. Overall, this fraction should be positive. This one on the left will be negative. Okay? When we got our equation here, this time our derivative has an x and a y in the answer, which means it's equal to negative x over whatever y is, if you could get y by itself. And in our example, we could get y by itself. We did that right here. We got y by itself by bringing it over to the other side and square rooting both sides. And we got plus or minus the square root of 16 minus x squared. So now if I rewrite this as plus or minus the square root of 16 minus x squared, is this answer not identical to what we found here? One was positive, one was negative. So if this one we could get y by itself, because we did, right? The next example that's coming up, you look at it and I say try to solve for y in that one, and you'll be like, yeah, no, it's not going to happen. So we can still get the tangent, but now if you want to find the tangent at a certain point, you not only have to plug in the x coordinate, you have to plug in the y coordinate as well. So on this circle, and here's a picture of it. Here's a picture of the circle that we just did. If you wanted to find the derivative at 0, 4, you would have to plug in 0 for x and the 4 for the y in order to find the slope at that point. If you wanted to find, right now, my point is at negative 1.18, 3.82. The slope of this tangent line is, well, I'd plug in negative 1.18 for x and 3.82 for y, and whatever 1.18 divided by 3.82 is the slope of that line. Which is pretty cool. But now you have to plug in both your x and your y coordinate to find your slope. If we drag this around to see what this actually looks like, it's kind of fun. I think it kind of looks like the lines on a basketball. Not all of them, but you've got, these lines do look appropriate from a two-dimensional look of a three-dimensional basketball. That would be the equation. The derivative of a circle becomes some of the lines on the basketball. That's pretty cool. No, I think they put the lines on a basketball because it looks nice. And most things that look nice usually tend to come up in mathematics as something that would naturally occur, which is kind of cool. No, I'm pretty sure the person that was saying, oh, I want to make a nice basketball, is like calculus major in university. Usually, sometimes those things don't go together. Sometimes they do. But so that's pretty cool that you can now derive something separately. In fact, we could have derived our old functions this way, like y equals 3x squared plus 5x. We could take the derivative with respect on the left side and the derivative with respect to x of the right side. Now, whatever has an x in it is just deriving like normal. So the right side, this would just be 6x plus 5. The left side, well, how would you do the derivative if you had just dy of y? It would just be 1, right? But it's a chain rule. So you're going to have your 1, and then what's the derivative of y with respect to x? It's going to be dy dx. It's just the y by itself. But what we're doing here is we're saying the outside function is the exponent of 1. The 1 comes out in front. You subtract 1, which just becomes 1. And then the derivative of the inside, because we have to say every time we see a y, that y is a function of x, even if we don't know what that function of x is. In this case, we do know what that function of x is. Y is equal to 3x squared plus 5x. And so then the derivative of y is 6x plus 5. So now that was a super simple example, but now we'll look at one that's not so simple. Okay? Y cubed is equal to 2x. And we could solve this one in two different ways. I'm going to solve it with implicit differentiation, and I'm going to solve it with our old techniques. If you were using your old techniques, because that's what you're more comfortable with, you would first get y by itself. In order to get y by itself, you would have to cube root both sides. Cube rooting both sides would do what? Be the same thing as having to the power 1/3. And if you wanted to find the derivative of this, the 1/3 would come out in front. You would subtract 1 from the exponent, and then there would be a chain rule, and the derivative of the inside would be times by 2. Using implicit differentiation, you're going to derive everything with respect to x on both sides. What it ends up doing is you do the derivative of 3y as 3y squared, because that's like the outside function is a cubed. The chain rule says you bring the 3 out in front, you subtract 1 from the exponent, keep the inside the same. Then you multiply by the derivative of the inside. Well, what is the derivative of the inside? Because it's just y, what's the derivative? The derivative is the derivative. That's what we're trying to find. We're trying to find the derivative of y with respect to x. And on the other side, d dx of 2x would just be 2. Now, if you wanted to solve for dy dx, you get 2 over 3y squared. Now, the trick is, how are these two things the same? Okay? Well, on this side, can you see that if I have the fraction 2/3 and this 2x to the negative 2/3 is the same thing as 2x to the positive 2/3 on the bottom, which is the same thing as the cube root of x all squared. or sorry, the cube root of 2x all squared, because that's what that 2/3 does. Now the reason I'm writing it like that is, can you see that that is y? And that is the same thing that we have over here. But instead of having to write it in a complicated form with just x's, now we've got our equations with x's and y's. It's just magical. Nice. That's the idea. Now this is nice because we can see why it's working with an equation that we can manipulate and get y by itself. But as you see in this next example, how would you get y by itself? You know, you could move the 3x to the 4 over and this y over to that side, but you would still have a y to the 7 and a y. But you're still going to have multiple expressions with y. It's going to be hard to get y equals and just x's on the other side. Well, you can't do it with just one function. Okay? It would have to be a multiple amount of functions, because every time that we write y by itself with x's, we are making a function. And a function passes a vertical line test. But what we saw with our circle doesn't pass a vertical line test. It's a relation. So you have this part, which was our plus, and this part, which is our negative, and both of those separated each makes single functions, but putting both of them together makes it not a function. So there is a way to take the function that we just had here and write one piece that's a function y equals, and another piece that's a different function y equals, and another piece that's a different function y equals, and do all of those separately, and then graph them all, and you get something that is probably not going to be a function, because you have a whole bunch of functions graphed at the same time. So chances are it's not going to be a function in the end. Now, since we can't get y by itself, we are still able to do implicit differentiations. We derive everything with respect to x. This is going to be easy. So we're going to do d dx of 3x to the 4, and we're going to do d dx of this term, x cubed y, and we're going to do d dx of 15. Find the derivative of that, and we're going to do the derivative of y to the 7. Now this is a step that you probably won't show when you're doing your work. You're just going to go right to this next step and start doing the derivative. Can you do the derivative of 3x to the 4? Yes, that's easy. It's going to be 12x cubed. Can you do the derivative of x cubed y? Ooh, this gets a little bit more complicated. This is going to be, because this is one function multiplied by y, which is another function. So it's going to be a product rule. How do we do our product rule? And since we're subtracting, I'm going to do a big set of brackets, because what's going to happen? We're going to keep one the same, do the derivative of the second one. What's the derivative of y? dy dx. Plus, keep the other one the same, so we keep y the same. What's the derivative of x cubed? 3x squared. Equals, the derivative of 15 is just 0. The derivative of negative y to the 7th, well, it would be a chain rule. The 7 would come out in front, and then the derivative of the inside is dy dx. So we always, when we see a y, we always think of chain rule. You can do your derivatives just like normal, and then remember what the derivative of y is dy dx, or the derivative of y. Now, we have to go and manipulate this equation and get dy dx by itself. So whichever terms have a dy dx, we're going to put on one side. Whatever terms don't have a dy dx, we're going to move to the other side. We're going to factor out our dy dx, and then we're going to be able to solve. So what's that going to look like? I'm going to keep my x cubed dy dx on this side. I'm going to move my 7y to the 6 dy dx to the left side. I'm going to move everything else to the right side. So the 12x cubed is going to be negative 12x cubed. Can you see that your y times 3x squared, which is positive inside the brackets, is going to get multiplied by this negative outside, making it negative on the left side when you add it to both sides. It'll be plus on both sides. Yes? Because when we did the derivative from here to here, yeah, so that 6 is part of the exponent of the y. Now we can factor out dy dx, leaving us with negative x cubed plus 7y to the 6. And to get dy dx all by itself, we just have to divide by negative x cubed plus 7y to the 6. Whew. So you want to see what this looks like? Yeah. This yx cubed on the right side comes from a mistake. Thank you. It comes from this y3x squared, and I don't know why I changed it. I don't know why, but it should be y3x squared. So we could write that as 3x squared y in the end, and it should be that way all the way through. Thank you for noticing that. I'd like to say I did that on purpose to see if you were paying attention, but I did not. Does that make more sense? Yeah, implicit differentiation doesn't go naturally with the brain. So, do you want me to scroll back up a bit here? Is that far enough? This one looks like, so here is the graph of this one. It's kind of interesting. What's interesting about this graph is it almost looks like a function, except in these parts here, we're going to find out it actually bends back in time, so that's not really a function. If we want to know what that derivative that we just drew looked like. So this is something a person that's trying to design a time machine? I don't know if it's a time machine kind of problem or not, but yeah, so sort of looks like almost like we've got asymptotes in there. But I think right here, doesn't that look like a negative slope? So we're going back in time in that little section there. And there, now you can see that the derivative actually overlaps as well, making it not a function. But still a pretty looking graph, I guess. Yeah. What's that? So first of all, I'm just going to take the time to rewrite this one so everything is in a form that's easy to do the derivative of. Still ugly? And now you're going to differentiate everything with respect to x. Well, the x squared is just going to be 2x. The y to the 1/3, 1/3 y to the negative 2/3. And then what's the derivative of y? dy dx. So it's important that you understand what's happening, and you might have to, go back and rewatch this video a couple of times and really try to ponder it. But a lot of times, the first time people are doing implicit differentiation, they're also just learning, oh, every time I have a y, once I do the derivative, I multiply by dy dx at the end, and that's true, because that's what the chain rule says you should do. Okay. Here, we have a product rule, because you have 3x to the 4th times by a y cubed. So you're going to keep one the same, multiply by the derivative of the other one, which will be 3y squared, and the chain rule would have a dy dx, and I'm going to run out of space. Nope, maybe not. Plus, keep the other one the same, which is the y cubed, multiply by the derivative of 3x to the 4th, which will be 12x cubed, plus the derivative of 8 is just 0. Whew. Yes? I don't know who decided to use x's and y's. Do you think this would be an easier question if we were finding dA dB? Or dW du, or whatever letters we could change this. dW and du would be hard because they both are very similar and they sound du and dV, yes. So again, at this point, we're going to take all of our terms that have a dy dx and have them on one side of our equation. So I'll subtract. Are you okay with me multiplying those three together? Get 9 and x4y squared dy dx. And on the right-hand side, we're going to have our 12x cubed y cubed, and I'm going to subtract the 2x. So this that I've underlined in green moved over to here. And I just multiplied the 3's together. Yeah. And this that I've underlined in red, I moved over to this side of the equation so that my terms with the dy dx were on one side of the equation. My terms without were on the other side, and the reason I like that is so that I can factor out a dy dx, leaving me with 1/3 y to the negative 2/3 minus 9x to the 4y squared. After you write all this, you know what? When you look at your notes, it does look impressive, right? There's a lot of derivatives look really impressive because if you don't know the derivative rules, a person looks and says, I have no idea how you went from this step to this step, because there is no, it just doesn't make any sense, right? Now, I'm not saying that you pull this out at parties and impress your friends, because that may not go over so well, but you can feel good that now when you watch some of those movies and they have like calculus on the board in the background to make it look like a really impressive university class, you'll be like, yeah, I see what, it's not that complicated.
If you wanted to scare us at the first class, I would have dropped it.
I should have shown you this the first class then, eh? Yeah.
Right there.
It's not so bad.
You learn it in p-tab, first thing you see in p-tab.
There you go.
Oh, there's more. I would have to.
Yes.
Did you ever have to simplify the fraction? Like in the test or whatever?
No, you would leave it like that. Yeah. The book will simplify it. So you still are going to practice. You're still going to practice your show that kind of idea when you're doing your homework. Well, you could factor out an x out of the top. You could factor. Yeah, you could factor to 2. And this is a complex fraction because of the 3, so you should multiply top and bottom by 3 and work with that a little bit. But we're going to leave it like that. I do have this graph for you to see if you want. It's kind of got some kind of wiggly thing right in there. Kind of nasty derivative thing happening in there, right? There we go. There's our derivative.
Thank God we never have to draw those.
Yeah.
We do better laughing graphing.
We are going to do graphing, but I will not ask you to graph this function by hand. And the derivative.
Maybe you could make the whole exam
Just
just that.
this.
We're still not finished.
There we go.
Promise class?
No. So there's some to practice. We'll take some time.
My weekend.
We'll take some time tomorrow to practice those.